In this section, we want to talk about linear programming. What is linear programming? The linear programming is a mathematical process to make a decision, for some real problems, real life problem. Okay, so here we only introduce a way which is called geometric approach. So before we introduce the linear programming, formally let's look at this problem. So if we have a function z is equal to 5x plus 4y, for example. Okay. So if we take the different value of z, if we put some constant z into z, then we have a linear equation, right? So we can draw the graph on our xy plane. This is x, this is y, right? So for example, so why this is true? It represents a straight line if you fix a z, okay? So why this is true? If you solve for y for this equation, you have 4y is equal to negative 5x plus z, right? And then y equals negative 5 over 4x plus z over 4. So you can say this is called the slope intercept form, right? So this z over 4 represents the y-intercept. So it represents a straight line if z is a constant. So the slope is negative, so it must be this direction. It must be this one, right? For example, for this one. And this would be the y-intercept, z over 4. So if we take z to be, for example, if here is z equals 8, this line, so here is 2, right? If this is z equals 8. So this is the line you have, okay? And if z equals 6, so then it would be 6 over 4 would be 3 over 2. So this is 3 over 2. Then you have another line, we use another color, which is parallel to this line because they have the same slope, right? So this would be z equals 6. If z equals 4, so z equals 4, so this slope, the y-intercept would be 4 over 4. 4 over 4 would be 1, right? We use another color. So if this is 1, okay, this is 3 over 2. And this is 1. So we have this line. So you can see that for this example, z equals 5x plus 4y. For the different choice of z, you have the different lines, right? Then you can see that the line is go downward, okay, go this way if z is decreasing, right? So here, this is z equals 8, this is z equals the red line, z equals 6, and this is the z equals 4. So all the points on the blue line, we will always take z equals 4. All the points on the red line, we will always take the value z equals 6. For all the points on the purple line, then the value of z would be 8, right? So if we have some region, which is called a feasible region, we talked last time, which is the region we only considered, okay, for example, for this region. Right. If your function z equals for this feasible region. So that means we only consider the xy in this region, in this shaded region, including the boundary. Okay, if this is z equals 5x plus 4y, okay, it will represent a straight line. We use green color. Okay, it will represent a straight line, right? And as z is decreasing, it will go in this way, right? We just state it will go this way. This is z is decreasing. And these dashed lines are parallel to each other. Okay. But we only consider this region, this shaded region. So we only consider the line between these two lines. This is the first line touches at this corner, this region at this corner. Oh, and this line. This is the line will leave this region touches at this corner, right? We will consider all the lines, all the z values between the purple line and the red line, right? So for these lines, between the purple line and the red lines, the purple line have the largest z value, right? And the red line has the smallest z value, right? The reason is we state here for this specific equation, and it will go down as z is decreasing. So the other lines we will not consider because we only consider the values of the xy values in this region. We don't consider other values outside this region. So this is the boundary, right? This is the greatest z value, and this is gives you this line at this point. This point will gives you for this line will gives you the maximum, the minimum, the smallest z value, and this point will give you the largest, because this point is on the line, right? So this point is the point to make z to be the greatest number. Okay, so this is give you a way which is called the geometric method or geometric approach. Okay, so now let's look at this example. Okay, so for this example, we see that the maximum value of z and the minimum value of z only happens at the corner. Okay, so this gives you an idea how to find the maximum values of z or the minimum values of z for a feasible region, which means the xy should be in this region. We just need to check the z values at the corner, okay, at the corner. So now let's look at the next example. Okay, in this example, we consider z equals 5x plus 4y, okay, which is the same as the previous one. And the region is this triangle. We have the corner of the triangle, which is 8, 15, 5, 6, and 49. Okay. So we want to know. So this is the region which is called the bounded region because it has a boundary, right? Bounded region. It's bounded. Okay. So we want to find. So the question is if we can find the minimum value of z or the maximum value of z, or the question is if they exist or not, right? For this equation, right, for this equation, we know that if we fix a z as a number, then this will give you a line which has a negative slope, right, negative slope. Because you can write this one as a y equals negative 5 over 4x plus z over 4, right? So you see the slope is negative 5 over 4. So it will go this direction, right? This would be this direction. So, and we know that it will go down if z is decreasing. So z is decreasing. Z is decreasing. So we can see this problem. So from the previous example, we know that it only happens at the corner, okay? So we just need to test the corner value, okay? So this one, you can imagine that this would be this point will give you which is called the smallest z value, right? The other 2 points, maybe one of them will give you the maximum value of z, but we don't know. So the minimum value of z and the maximum value of z for this bounded region always exist, okay? So minimum or maximum value of z exists for a bounded feasible region. Feasible region means we only consider the x, y value lies in the shaded region. Okay, so we need to test, right? So we draw a table. We put the point. This would be 8, 15. And this is the 14, 9, and 5, 6. Okay, so these are 3 corners of this region. And this is the z values. Okay, z equals what? So here is z is equal to for 8, 15, z is equal to x equals 8, y equals 15. So it's 5 times 8 plus 4 times 15. If you use a calculator, it would be, this is the 60, this is the 40, so it's 100. Okay, and z equals, for this point is 5 times 14 plus 4 times 9. 14 times 5 equals 70. 70 plus 4 times 9 is 36. So 106, right? And for this part, this would be 5 times 5 plus 4 times 6. This is 25, and this would be 24, so it plus together 49. Okay. So in other words, this point gives you the maximum value. Right? This point will give you the maximum z value, and this point will give you the minimum z value, right? We use different colors. So this is the minimum z values at this point, which is z equals 49. This is z equals 49. And at this point, this line represents z equals 106. 106. Okay? And you have another line which goes through this point. this point, this is represent z equals 100. Okay, so this gives you that, so you have the maximum value of z, so we use the max of z is equal to 106, and the minimum value of z, mean of z, is equal to 49. Okay. So now let's look at the next example.